Hello, and welcome to the second tutorial in our series about MBX. Now that we've compiled MBX, in this tutorial, I'm going to show you how to use some of the standalone executables, such as calculating the single point energies or the normal modes. I have our previous compiled version of MBX here. I also have two example XYZ files and an mbx.json. So let's take a quick look at what I have in these XYZ files. For this example today, I just have water molecules that are pretty crude. So it's just an oxygen at the origin, a hydrogen 1 angstrom away on the x-axis, and another hydrogen 1 angstrom away on the y-axis. So these are unoptimized configurations. And then for 3H2O, I just have 3 of these unoptimized waters. Okay, so if I take a look at MBX, this is what we compiled last time. And if we look at bin specifically, we get to see some of the executables that we compiled last time and have available for us. In the tutorial today, I'm going to go over single point, which computes the single point energy for the configurations you give it, mb-decomp, which performs the many-body decomposition, and this is able to give you like the pairwise energies, 3-body energies, so on and so forth. We have optimize, which will take your initial structure and try to do some optimizations so it can try to find the optimal structure. Normal modes to compute what the normal modes for your molecules are, and order frames, which I will not be going over in this tutorial, but this is if you have a bunch of frames, order frames will compute the single point energy for each of the frames, and then it will order the frames from lowest to highest energy. Also, we have the IPy driver. This is the driver if you want to use MBX with IPy. This is what will provide those many body energies into IPy. Okay, so now that we have these executables, we're going to first start with single point to calculate what is the energy of a configuration. So in order to use these executables, so like if I try to do MBX in single point, we can see that single point has a usage of the executable. It needs a mb-nrg or .nrg file, and optionally an mbx.json file. You may be wondering, well, what's an .mb-nrg file? Or why do I need this? Why can't I just pass in XYZ? So the issue is, with an XYZ, you only have given it atoms, but XYZ files do not contain information about molecules. So instead, we have a file format mb-nrg or .nrg that's able to add this additional information about the molecules so that our standalone scripts can understand the monomers and molecules that you're giving it. In order to do this, we have some helpful format conversion scripts located in MBX, this whole folder here, scripts, format conversion. Let's do an ls. And we can see we have XYZ to lamp data file, XYZ to mb-nrg or .nrg format. We can also convert back from mb-nrg format back to XYZ, and also a lamp's trajectory file back to XYZ for some use cases. We're going to go to Python 3. We're going to use the format conversion script XYZ to energy, and we're going to pass in this one water XYZ file, run it, and now we have it in this .nrg format. So if we take a look at this file, we can see that the core of it is similar to XYZ in terms of the coordinates, but we now have added additional information about what's the monomer and also which monomers belong to which molecules. So these three atoms belong in the monomer H2O, which are part of the same molecule. If we do the format conversion again, but for the other example I have, so we take the 3 H2O. Oops, that's a misspell. And now we take a look at the 3H2O.energy. We can see that we now can have 3 separate H2O monomers. And these are in 3 separate molecules. And this will allow us later to do many-body decompositions on the system. Before running those executables, I want to briefly go over the mbx.json configuration file. This contains a bunch of parameters that are used to configure MBX. Most of them, the default values we give them are good, but there are a few key ones we want you to pay attention to before running a calculation or simulation. So I'll go over all the parameters and point out the ones you should definitely double check before running something. So the first one is the box. If you're running a gas phase simulation, you'll just have it empty with just the square brackets. But if you're running a simulation or calculation in periodic conditions, you need to fill out the box vectors here, AX through CZ. So if you have like a cubic box, you might define the 3 vectors like this. This is a box with a 21 angstrom side. Another parameter you should check is the real space cutoff. Usually for a periodic simulation, a value of 9 is good. And that means that anything below 9 is handled in the real space, while everything outside of that distance is handled using PME. But do note that for a gas phase simulation, it should be set to a large number so that all of the calculations are done in the real space. So if you have like a 20 angstrom box, we usually put something like 100 angstroms or something large like that. For the 2-body cutoff and 3-body cutoff, these values depend on what you're simulating. If you're only simulating water, you can use these smaller values, and having these cutoffs smaller speeds up the simulation a bit. But for pretty much anything else, you need to be more careful and use a larger cutoff, such as 9 angstroms for the 2-body cutoff and 7 angstroms for the 3-body cutoff. In terms of these cutoffs, if you happen to use these larger cutoffs for water, that's totally fine. It'll just be a bit slower than usual. But if your cutoff is too short, that will likely cause issues with your simulations or calculations and introduce error. So if you're using water, use these smaller values. But if you're not sure or you're simulating something aside from water, please use these larger cutoffs. Okay. The next ones, dipole tolerance, dipole max iterations, and dipole method. These are related to the self-consistent solving of the dipoles. The values here, for most end users, they don't need to adjust these values. The default ones we give in the examples should be fine. Okay, next up is the alpha Ewald elec and alpha Ewald disp. So these are the alpha used for the reciprocal space. When you're running a gas phase calculation, they should be set to 0. And if it's instead in PBE, it should be set to 0.6. So that's something you should check depending on your simulation and should make sure is correct. For grid density and spline order, those values are here. You don't usually need to modify those. And then the last two, ignore 2B poly and ignore 3B poly. This is if you want to run a simulation where you're disabling some of the many-body contributions in order to, for example, know like what is caused by that contribution specifically. So you can specify one or multiple polynomials in this notation by adding one or more inner square brackets with the monomers. So you could have like NaH2O and then ClH2O if you wanted to turn off those interactions specifically. And it's very similar for the 3-body. And if you're using IPy, there's this optional section here with localhost and port. This is given to the IPy driver and is used to run your IPy simulation. If you're not using IPy, that section will be ignored. And as a recap for the things you should check depending on your simulation, the ones you will be changing are the box, real space cutoff, 2-body and 3-body cutoff as previously described, and the alpha ewald. And of those 5, the box, real space cutoff, and the alpha ewald, elec, and dispersion, these are the ones you should always double check when going between gas phase versus periodic boundary condition simulations. So again, whether in the gas phase for box you specify nothing, have a very large real space cutoff, and turn off these alpha ewald elec and alpha ewald disp. But if the periodic boundary conditions are on, you need to specify the box, make sure the real space cutoff is set to something reasonable like 9 angstroms, and that you turn on alpha ewald elec and alpha ewald disp. Okay, so we now have our 2 XYZ files. We also now have the 2 mb-nrg or .nrg files, and we're now going to first start off with a single point. So back into MBX and the bin, single point. Again, we need the .nrg file and optionally an mbx.json as we've previously specified. So I'm going to now pass in the 1h2o.nrg file, and this prints out the energy with the units of kcal per mole. And then let's do the same for the other example. Okay, and these are printing out the energies. Do note that for the single water molecule here, since we don't have any intermolecular interactions because there's only one molecule, this energy is representing the distortion energy. In contrast, with the 3 water molecules, we have both the intra and intermolecular interactions. Okay, so that's the single point executable. Okay, and now for the other executables we have, we're now going to do the mb-decomp executable. This will help us get the decomposition of the energy to the different many-body terms. So let's call mb-decomp, and it'll give us some information on how we use this executable. So it has a similar usage to the other one. We pass in the .nrg file and the mbx.json. And we also have options such as verbose and printing out the XYZ for the different subsystem. Okay, so first let's use it normally. So I'm going to do 1h2o.nrg, and it prints out just a single energy. This is because we only have the 1-body term, so we only have one term printed out. Also note, if you want to use the mbx.json file, you just add it on at the end. Okay, now let's try the more interesting case of 3 waters. Okay, so what this is doing is printing out the 1-body energies, the 2-body energies, and the 3-body energies, the 3-body energy for these systems. To get a better view what is going on underneath, I'm going to turn on verbose mode by adding in this V flag as specified here and here. Okay, so this organizes it slightly simpler. We can see now the specific indices for the water molecules, molecule 0, 1, and 2, the interactions between 0, 1, 0, 2, 1, 2, and then the 3-body interaction between 0, 1, 2, in kcal-promol. So that's the many-body decomposition executable. It's really useful when you want to kind of see these different interactions. So we can see that between molecules 0 and 1 and 0 and 2, those interactions are the same because those molecules are the same distance away. But for 1 and 2, which are further away, the two-body interaction is much weaker. Okay. Now I'm going to show the optimize executable. So the optimize executable, again, is used to find the optimized structure for a molecule. So currently, the water molecules I have here are at 90 degrees, which is not a natural angle for them. So here we have the usage statement. So as usual, we can pass in the energy file, the mbx.json optionally, and we have a few different options because this is an optimized, so it does have iterations to try to find the ideal solution. So you may need to modify these options if you have a tricky structure to optimize. But for right now, we're just going to do a single water molecule. Excellent. So we have optimized the water structure from this original one to optimize.xyz. And as we can see here, the angle is now a much more reasonable 104 for this water molecule. We can also do this for 3 waters. And this will be more complicated because you have all 3 molecules. You have to care about the angles in all of them and the position of the 3 different waters relative to each other. Okay, we can now see that the optimized structure has caused the water molecules to move and rotate a bit so that the water molecules are able to hydrogen bond better. And now that we have the optimized structures, we're able to use the normal modes executable in order to calculate the frequencies. So if we look at mbx bin normal modes, we can see that we need to pass in the optimize.mb-nrg file format and mbx.json, and then printing the displacements. So mbx bin normal modes, I'm going to pass in optimized 1. So I took the optimize XYZ and used the format conversion script from earlier. I added the mbx.jsons. And since I don't want to print the displacements, I just type 0. I hit enter, and GSL is then able to compute the frequencies for us. Thank you for watching this tutorial. Today, we learned how to use the format conversion to .nrg format, learned what the parameters in the mbx.json file are, and then we used the single point mbdcomp, optimize, and normal modes executables included in standalone MBX. In the next tutorial, we will go over how to compile MBX with lamps, and then in the 4th tutorial, we'll talk about how to then use MBX plus lamps to run simulations. Thanks again for watching, and happy simulating.